Projectile Motion, and I'm Royce Kim. The purpose of this lab is to analyze the motion of the object which is thrown and acts like a projectile. The observed motion will be compared to two models, one considering gravity solely and the other with both gravity and drag force. The object is a bracelet, observation held by tracker, prediction done by glow script. So this lab will help demonstrate the principles of Newton's second law and the effects of the drag force. So the system is bracelet and the surrounding might be the person throwing it, the air, and the gravity, and much more. So the fundamental principle will be Newton's second law, which is a system's change in momentum is proportional to the net force applied. The equation is on the right side, and the gravitational force, which is attractive force that pulls objects with mass towards each other. And the object near the Earth will follow this equation. And lastly, drag force, which is a resistive force that opposes the motion of an object through a fluid. So if I give you a brief preview, the computational model overestimates the position of the bracelet, but considering the drag force increases the precision of the prediction. So this is the tracker video. If I analyze the tracker, the total time will be 0.567 seconds, and I calculated the initial velocity. But I want to note that since I set the points by hand, origin is not the initial position. So while making computational model, I set the ball mass, which was 17.585 gram into kilogram, and I set the position and velocity. And since the time frame, I considered delta t as 1/30th and j hat as the y direction, and make a t and make this equation, which is the force will be the negative ball mass times g times j hat, and the F net in this case will be solely gravitational force only. And I wrote velocity update form and position update form. So this is the result. So if I do the observed versus predicted motion, we can see as t gets larger, the model predicts the object to be further, which means there is an additional force acting, which is air resistant, which we will calculate by drag force. And the second computational model, which I include gravitational force and drag force, I calculated experimented B to be 0.0016, and I added drag force and added this equation, which is F net is gravitational force plus drag force. So if I look at this graph, even though the both model overestimates the observation, but still the drag force included model has increased in the precision. So the possible errors can be the outside forces, which AC was blowing air out, and also the shape of bracelet. Bracelet was not spherical, which can cause to error, and the position of tracking. So video might be recorded and then certain angle, and the initial position it's not at the origin, and by manually selecting center of mass could have led to errors. So, do any of your models predict the terminal velocity? I would say not really. Throwing the object from the greater height would allow more time for air resistance to build, thus leading to near zero net force. And what would happen to terminal velocity if the object was initially thrown straight up? So only the vertical component of the initial velocity determines the time it takes for the ball to reach the ground. So when thrown straight up, the initial speed will solely be vertical component of the initial velocity. Therefore, the ball reaches a higher maximum height and would take more time to reach the ground from its taller height. Thank you for watching.